In this lecture, we are going to look at two of my favorite criteria for model performance of classification models. The first is the Gini coefficient, while the second, Kolmogorov-Smirnov. They are well established and widely accepted in the credit risk modeling community. Gini coefficient was created as a measure of income inequality. More precisely, it was originally used to measure the inequality between rich and poor individuals in an economy. If you have studied economics, you have probably stumbled upon it. In credit risk modeling, Gini is utilized with the same purpose: to measure inequality between non-defaulted or good borrowers and defaulted or bad borrowers in a population. The Gini coefficient is measured by plotting the cumulative proportion of defaulted or bad borrowers as a function of the cumulative proportion of all borrowers. It looks something like this. As a prerequisite, the borrowers must be in ascending order by estimated probability of being good from the PD model. The Gini coefficient is the percentage of the area above the secondary diagonal line, enclosed between this concave curve and the secondary diagonal line. The greater the area, the better the model. Okay. The second criterion, Kolmogorov-Smirnov, shows to what extent the model separates the actual good borrowers from the actual bad borrowers. It is measured by looking at the cumulative distributions of actual good borrowers and actual bad borrowers with respect to the estimated probabilities of being good and bad by our model. Kolmogorov-Smirnov, or KS in short, is the maximum difference between the cumulative distribution functions of good and bad borrowers with respect to predicted probabilities. The greater this difference, the better the model. In order to plot the Gini graph for our data, first, we need to order our data frame that contains the targets and the probabilities by the estimated probabilities in ascending order. So, let df actual predicted probs be equal to df actual predicted probs dot sort values by y hat test proba. Now we can take a look at the head and the tail of the data frame. Alright, we have successfully sorted it by the predicted probabilities in ascending order. Next, in order to calculate cumulative proportions, we need to reindex the data frame as it is sorted now. So we need the row with the lowest y hat test proba to have an index of 0, the next one 1, and so on. We achieve that by using the rest index method on the data frame. I'll simply override it. Notice that this method not only created new indexes for our data frame, but saved the old ones in a new column in the data frame itself called index. This will be very useful in case we want to connect any of the subsequent calculations to the other data frames. Alright, to make plots of our model performance criteria, we need the cumulative percentage of the total population, the cumulative percentage of good borrowers, and the cumulative percentage of bad borrowers. Let's start by calculating the numbers first. The cumulative number of total borrowers on each row is the index of the row plus 1. The cumulative number of good borrowers on each row is the total number of ones in the loan data target test, variable up to that row. Since the loan data target test variable contains only zeros and ones, this can be expressed as the sum of all rows from the loan data target test variable up to that row. So conceptually, that is not hard. Luckily for us, coding won't be either, as Pandas has a dedicated method that sums a variable up to a row is called cumSum, short for cumulative sum. And, last but not least, the total number of bad borrowers up to a row is the total number of zeros in the loan data target test variable up to that row. We can't sum the zeros as we did with the ones because the total will always be 0. But we know that the loan data target test contains only zeros and ones. We also know the total number of ones up to a row. Plus, we are aware of the total number of borrowers up to every row. So, the total number of bad borrowers on every row can be calculated as the difference between the total number of borrowers up to that row and the total number of good borrowers up to that row. Great! We have all the information we need. To make it more usable for probabilities distribution plots, it makes sense to find the respective cumulative proportions. The cumulative proportions are the numbers divided by their own total. Therefore, the cumulative proportion of all borrowers on every row is the total number of borrowers up to that row divided by the total number of borrowers altogether. An easy parametrized way to find the total number of borrowers is to take the shape on axis 0 of the data frame. What about the cumulation proportion of good borrowers? It is equal to the good borrowers on every row divided by the total number of good borrowers altogether, or the sum of the loan data targets test variable. Respectively, the cumulative proportion of bad borrowers is the total number of bad borrowers on each row divided by the total number of borrowers altogether. The total number of bad borrowers altogether is the difference between the total number of borrowers and the total number of good borrowers. That is, the element with an index of 0 from the shape of the DF actual predicted probs minus the sum of the loan data targets test variable. Perfect. Now we really have everything we need to plot Gini and Kolmogorov-Smirnov. Let's start with Gini. As we mentioned, it is a plot of the cumulative percentage of bad borrowers as a function of the cumulative percentage of all borrowers. That's why we should plot the cumulative percentage of all borrowers on the x-axis and the cumulative percentage of bad borrowers on the y-axis. It is useful to also draw a diagonal line here. Similar to the ROC curve, it shows what would have happened if we were guessing and classifying good and bad borrowers randomly instead of using a statistical model. So the Gini coefficient is the proportion of the area enclosed by this diagonal and our Gini curve from the area of this upper triangle here, defined by the diagonal line. There is an analytical formula to calculate Gini, as well as other graphical methods. But, as you may have noticed, the Gini curve resembles the area under the ROC curve quite a lot. Actually, the two represent different ways to plot the same thing. Gini can be expressed as a function of the area under the curve and vice versa. More precisely, Gini equals 2 times the area under the curve minus 1. In fact, let's use that formula to calculate Gini coefficient for our model. Alright, our Gini is about 40.43%. Not bad. Time for our second measure, Ks. The Kolmogorov-Smirnov statistics measures the distance between two cumulative distribution functions. The further apart they are, the better the underlying feature differentiates them. In our case, we are interested in the difference between the cumulative distribution functions of actual good borrowers and actual bad borrowers, plotted by estimated probability of being a good borrower. If our model was perfect, it would estimate such probability of being a good borrower that it would set the two cumulative distributions as far from one another as possible. Then the Ks statistic would be 1. In the opposite case, if our model was as good as predicting by chance, the two cumulative distributions wouldn't differ with respect to estimated probability of being a good borrower, and the Ks would be 0. We need to plot the cumulative distribution functions of good borrowers and bad borrowers with respect to estimated model probability of being a good borrower. First, we should plot the estimated model probability of being good on the x-axis and the cumulative percentage of bad borrowers on the y-axis. Let's color this line in red. Second, we plot the estimated model probability of being good on the x-axis and the cumulative percentage of good borrowers on the y-axis. Let's color this line in blue. Great! So these are the two cumulative distribution functions. The Kolmogorov-Smirnov criterion is the maximum difference between the red and the blue curve. We can get a pretty good idea where it is and how much it is in magnitude from the graph. However, we can also calculate it from the data frame containing the cumulative proportions. It is equal to the maximum of the difference between the cumulative percentage of bad borrowers and the cumulative percentage of good borrowers. Okay, the result that we get for the Kolmogorov-Smirnov is about 0.3. The value isn't too high. It doesn't get close to 1. However, it is significantly greater than 0. This value shows that, as we can see on the graph, the two cumulative distribution functions are sufficiently far away from each other that the model has satisfactory predictive power. Okay, very good. See you in the next lecture.